We're back to finding the integrals that are not over triple integrals that are not over a box. So the region of integration is not a box, but it has other shapes. So the first thing is that we want to discuss either in one of the direction, analogous to what we found in the double integral. We want to find in one direction that only two elementary functions are the bounds. In here, for example, if I draw to the z direction, I see that the surface z equal to u1 xy and z equal to u2 xy are the lower and upper bound. They're both elementary functions. So the interesting part of that is that I can set up an iterated integral with these two as the bounds for and z integration with respect to z. So that's the first thing that we do. We find one way that is simple, and then we go about working it like that. And so u1 of x and y and u2 of x and y are the bounds, and we integrate f of x and y and z, which is whatever density function that is, dz. Now, the next step is I have to figure out whether the outer limits are going to be. So the way this is set up, after we find the direction of the simple region, then we find the projection of the solid on the plane that contains the other two and axis, basically. So in here, I'm projecting this over x and y plane, and I find d, and that d is going to be the d that you do the double integral that is there outside. So you find a single integral for the inside, and then the two outer ones become a double integral. You do exactly how you do it with a double integral. So there are a few notation in here I want to mention. This means belong to. That means x, y, z belong to the solid E. In here, when I'm talking about domain D, then it's x and y values such that x and y and z belong to E. And so the other way of writing the solid is that x, y, z such that x and y is in the domain, the outer domain, and z is between the u1 and u2 of x and y. And so that's how we actually integrate, and we figure out the inner integral in here. The output of the inner integral, this circled one here, is going to be a function of x and y, as you notice, and then the outer two are going to be the outer two integrals are going to be with respect to x and y, so it works that way. Now, and how does this work for x simple solid or y simple solid? Again, for x simple solid, you go to the direction of x, and then there should be a lower bound and upper bound in that direction. And so x equal to u1 of y and z is the lower bound, and x equal to u2 of y and z are the upper bound, the two elementary functions there. Again, you want to find the projection over the plane that contains the other two axes, which would be in this case y and z. And that domain helps you set up the outer integral. If it's y simple, what do we do? This time, again, in the direction of y, you have to have two surfaces that make the upper and lower bound. In here, again, we call them u1 of x and z because y is the direction, and u2 of y and z as x and z because, again, y is the direction of the inner. And so that's the domain. And so the next slide, we're going to discuss one of the examples that goes with this. Now we want to find the volume of E, where E is the solid tetrahedron bounded by 4 planes. X equal to, the first one is x equal to 0, which is the YZ plane. And then we have y equal to 0, which is XZ plane. And then we have z equal to 0, which is the XY plane. And then we have this plane that is not any of those. It's just a plane, and it seems that it is intercepting all the axes. So again, I just said intercepting all the other axes. How do I graph this? If you remember from equations of the lines, you would find 2 points, or you find the intercepts. In case that something is intercepting, it's easy to just find if a plane is intercepting all these XYZ planes, XYZ axes, it's easier to find those intercept and then connect them together, and you know that plane is sitting there like that. How do I find those points though? Let's see. I'm trying to find a point, and if I'm looking at a point on the x-axis, that means y and z are equal to 0. So I have to say x plus 0 equal to 1. That gives me x equal to 1. And then the same thing, if I want to find on y-axis, it should be z and x are 0. See, y-axis is perpendicular to those at the origin. And so it would be y equal to 1. And then a similar thing for z. So I have to set z equal to 1 is the intercept if I set x and y equal to 0. So then if I connect these together, I get this triangle, and it gives me the tetrahedron. Look, all the sides are triangles. So now that I have the tetrahedron, how do I set up the integrals? I have to figure out, see, I see there's a surface in the bottom, which is basically the surface in the bottom is the z equal to 0. And there's surface on top right here. And that comes from this plane. How do I do this? I'm trying to figure out which way is the simple, and my first instinct is usually to go with z, and it turns out z actually is the solid is actually z simple, and the lower surface is z equal to 0, and upper surface is x plus y plus z equal to 1. And so I can set up the most inner integral. But to set up the most inner integral, if it's z simple, then I have to actually have z equal to and z equal to. There's one z equal to. I have to make this z equal to. How do I do that? I solve for z over here. So z is equal to 1 minus x minus y. And then that would set up my most inner integral. That is from 0 to z equal to 1 minus x minus y. Remember, it says volume. For volume, where we're integrating over function y and dz. That's my most inner. Then I have to set up the outer ones. And so the two outer ones. How do I set up the two outer ones? Now, if you remember, inner ones was just knowing z simple and going from the most lower to upper. Outer ones were the projection over the plane that contains the other two axes. The plane that contains the other two axes is the xy plane, basically. And so now I have to figure out what the projection is here. I can kind of see that shape over there, though. It looks like a triangle. It's one over here and one over there. So I can connect that and I get the region. Let me see. Now that I have the region, I have to set up this double integral out here. with that, with those regions. And how do I do that? So what happens is that I have to decide which way is my, between the double integral, which one is my most inner and which one is the outer one. And I'm going to choose y direction to be most inner. And so basically I will get that my dA is going to become dy dx, and then y goes from 0 to this line. What is that line? And this point is the x-intercept is 1, y-intercept is 1. I can solve and get y equal to 1 minus x is that line. So I get 0 to 1 minus x. If you didn't have these points, the other way that you can figure this out is to remember, when you're looking at this region, it's the this line over here is the intercept of, it's the intersection of that plane with the xy plane. So intersection of that plane with xy plane. What is xy plane? Z equal to 0. So I can plug in 0 in here and get the same plane over there. And so I set up the most inner. So how do I go find the outer? Outer goes from 0 to 1. And so this becomes my integral. And then I have to start by integrating this one, which will give me z. And then I have to plug in 0 and 1 minus x minus y. That is just 1 minus x minus y. Then I integrate 0 to 1, 0 to 1 minus x of 1 minus x minus y, dy dx. And then this is going to give me the answer. And the answer is going to be 1/6.